Hello everyone, and welcome to our web seminar of the last of the year, the series of the Latin American Journal of Physics. My name is Diego Restrepo from Universidad Antioquia. Our speaker today is Pedro Machado from Instituto de Física, Teórica in Madrid, who will talk about dark matter. Pedro Machado did his PhD in Brazil in the Universidad de Sao Paulo, and the talk today is entitled Global Constraint on Vector Light Effective with Interaction. We are glad to have him here as our speaker today, and remind you that our discussion can be open to question through the Google question and answer system, or through our hashtag in Twitter that is written in my screen. I will now hand you over Pedro Machado and start the web seminar. Pedro.
All right, so let me share my screen. And is it working? Yes, right? All right, so just tell me if you can see my screen.
Yes, we
can.
Okay.
Let me put in free screen. All right, so yeah, I'm going to talk about this work that I did in collaboration with Matias Bleno, Pilar Coloma, Enrique Fernandez, and Brian Zaldivar, which is called Global Constraints on Vector-like Effective WIMP Interactions. So what we were asking ourselves actually is basically, what is the global status of the WIMP searches? I mean, I believe it is a meaningful first step to start to combine different data sets to see if this thing can tell us the most, the most possible information about dark matter that we can have, right? So looking at individual experiments is very important, but we believe that since dark matter is one of the greatest puzzles in high energy physics of our time, it's very important to have a global approach to this question, right? So the point is that different experiments, they are sensitive to different dark matter masses, dark matter annihilation channels, etc. So we want to analyze this global status of the WIMP search, but before doing that, we need to ask ourselves, how can we be model independent? And, well, making a long story short, we can't. In general grounds, there is a kind of an equilibrium between being general and being useful. If you're way too general, there are just so many open possibilities that is just useless. On the other hand, if you are too specific, well, maybe your bounds are going to be super restrictive in a very specific model that it doesn't give you the feeling of what is happening in general, right? So to stay, to equilibrate between being general and being useful, we decided to use effective field theory as our tool to study the WIMP scenario. So, of course, we are not going to study the whole WIMP standard model effective field theory parameter space because, as I told you, there's just too much stuff, too much freedom in this. But we are going to restrict ourselves to some corner of parameter space which we still believe that is meaningful. So our assumptions as for this first step in looking at the data in a global way are the following. So first, we assume that we are going to study vector couplings. Second, we assume that dark matter is a Dirac fermion. Well, we also assume that dark matter is a standard model singlet, which is reasonable. This is very important. The fourth point that we write explicitly gauge invariant operators. This is very important because sometimes when you're doing effective theory, you need to say what is the validity of your effective theory. So for instance, if you're looking at direct detection experiments, you could do an effective theory which is not SU2 cross U1 invariant, and there is no problem with that as long as you stick to energies below the electroweak scale, way below the electroweak scale. Since we are combining many different data sets, we need to be valid below and above electroweak scale. So we need to be gauge invariant in our operators. And the last point is that we are going to restrict ourselves to dimension 6 dark matter, fermion operators. So combining all these things, I'm basically telling you that we're going to study this kind of operators here, right? So you have a dark matter current, vector current, and a fermion vector current. So in the most general scenario, these fermions here, they can be all the standard model fermions. So for instance, they could be, right-handed leptons, left-handed leptons, right-handed quarks, left-handed quarks. And in the most general case, we have 15 couplings, right? We have couplings to right-handed electrons, muons, and taus, the three lepton doublets, right-handed up, charm, and top, right-handed down, strange, and bottom, and the quark doublets. To have a feeling of what could happen when we restrict ourselves to models, we decided to also study some sort of proxies. So in these proxies, they do not correspond to a UV completion, but in some sense they have the same ideas of some models that are in the market. For instance, we could study the leptophobic case, where dark matter does not couple to leptons at all. So we basically get this general model, we take away all the coupling to leptons, and we have only the 9 coupling to quarks. We could also study the leptophilic case, where dark matter does not couple to quarks, it only couples to leptons. So it's basically the complementary of the leptophobic scenario. And we decided to study 2 more cases, one which we call family model, which maybe it's easier to explain with a picture, which basically the whole family has one specific coupling. So we have basically 3 couplings, C1, C2, and C3, where each one corresponds to a whole family of fermions. And there is another, the last proxy, which is a flavor blind, which I can also explain with a picture. Basically, if you call the other one vertical model, let's say, this one would be an horizontal model. So we are saying that the coupling is family blind. It doesn't distinguish between family 1, family 2, and family 3. So basically, right-handed up-type quarks would have 1 coupling, right-handed down-type quarks would have 1 coupling, and so it goes. All right, so this is our approach to our approach to this question about the global status of dark matter, and to get our hands dirty, we need to tell the ingredients that we have to do this work, right? To cook this work. So the first one, which is very important, right, is the dark matter abundance, which we take from Planck. Then a second ingredient is the CMB constraints. The reference will be there. I'll not say any of these references, but they are going to be written all over the slides. So the CMB constraints, and what happens there is that dark matter annihilation could heat up the intergalactic medium, and this would affect the CMB. And since the CMB is very well measured, in principle, you can probe dark matter annihilation channels looking at the CMB. Another ingredient is Fermi-Lat, the study of dwarf galaxies, and the idea there again is that dwarf galaxies are dark matter dominated objects, which makes them very background free objects. So you look at these dwarf galaxies and you study the photons coming out of that, and the main idea is that if dark matter if dark matter annihilates to something, for instance, let's say B quarks, this B would hadronize, and the hadrons would further decay, etc. And in all this chain of hadronization and decays, you are going to produce eventually photons, and you could detect these photons. We also use the LHC direct searches. So this is basically a monojet search. So the idea is that you collide proton-proton, you produce one jet, and a pair of dark matter which escapes your detector. So this pair of dark matter is basically missing ET. So the signature at the LHC is one jet and missing ET. We also do the same with LEP direct searches, but in this case it's not monojets, but it's monophotons. So you have the plus and minus, which goes to one photon and a pair of dark matter particles. We include the AMS positron fraction. And the last point is that we use the two direct detection experiments, Lux and Edelweiss. So to cook all this, we basically use the following machinery. We use a CalcHep to implement the models. We use Micromegas to calculate for us the Relic abundance, etc. And Multinest just to segment the 1, 2, and 3 sigma regions of this parameter space, since it's a multidimensional parameter space and it's intrinsically degenerate. It's very important to use a good minimizer. Now, let me show you already our most important result. Then I'll go for details. Please interrupt me at any point if you have any questions. So our most important result is this. This basically I'm showing you the delta chi-square as a function of the mass of the dark matter, where I marginalize it over all parameters of each model. So if you look there, in the general and leptophilic models, you have that dark matter mass is around 20-something GeV. Below that, they are disfavored by data. So the general and the leptophilic models are very similar, and I will explain to you why very soon. While for the other models, you see that you start to disfavor dark matter masses below 50 or maybe 70 GeV, depending on the model. Before showing you the details of that, let me just say a few words about two important topics. So the Relic abundance, this is very important to say that we assume thermal Relic. If dark matter is produced non-thermally, things can be very different. Now, the important thing about the Relic abundance is that the coupling of dark matter to fermions will deplete the dark matter density, and it means that if the channel is open, that is, if the fermions are lighter than the dark matter, the Relic abundance will be sensitive to a sum of these couplings. So basically, the annihilation cross-section goes like, well, there are some factors which we don't really care right now, but it goes like coupling squared, and you have some weight function, some weight factor here, where this weight factor takes into account, for instance, the number of colors, or if you're talking about, let's say, doublets, it takes into account the 2 flavors inside the doublet, and so on. So basically, there is one variable which encodes most of the Relic density information, which is this weighted sum of the square of the couplings. So for instance, if you're talking about a right-handed up quark, the weight would be 3 because of 3 colors. If it's a quark doublet, the weight would be 3 times 2 because of 3 colors times ups and downs, so 2 flavors. And just one more detail. You're going to see that the bounds on first family quarks are not going to be very strong in general, and the reason is because in this approach, we are not putting any bias to what our models would prefer. So basically, we just put the parameters and let the fit decide where it wants to go. And naturally, if you're talking about direct detection, the fit will decide to go xenon phobic. So basically, the coupling to ups and downs will have some relative sign and relative sizes in such a way that when you scatter coherently into, let's say, xenon, the amplitude comes out 0, right? So you can see here that if you're not in the degenerate line where dark matter is xenon phobic, the bound is very stringent. But in this degenerate line, the bound is just way, it's just very bad. All right, so let me show you a bit in more detail what happens to one of these models. We are going to study the general one because it has more information, and later I'm going just to say some words about the other ones. So this plot, I'm showing you each coupling of the general model, right? So right-handed electrons, muons, and taus, the lepton doublets for first, second, and third family, quark doublets first, second, and third family, right-handed downs, right-handed ups, and the variable that encodes the relic abundance information. And these bars here, the blue bars correspond to 50 GeV dark matter, the green bar corresponds to 100 GeV dark matter, and the red bar corresponds to half a TeV dark matter, right? So the first point is that relic abundance sets the sigma C to be in this region here. So if you have a coupling which has weight 1, like the coupling to right-handed muons, if dark matter if the abundance can be given only by that coupling, it means that the bar will reach this dotted line of the sigma C variable here, right? So if the bar reaches here, it means that you can have the relic abundance only with that coupling turned on. If you cannot reach this bar, it means that this coupling turned on even when you go to the maximum value allowed by data, it does not give you the relic abundance. Notice that there is the weight factor, which is not in this coupling. So for instance, here you have a square root of 2 distance between this guy, the edge here and this dotted line, right? Because this is a doublet. So in these two cases, you can see clearly that the coupling to muons could give you the right relic abundance for 50 GeV dark matter. Now, the question is why the other couplings looks like they cannot give you the relic abundance. So let's take a look at the data. For instance, we fitted AMS data, so we have our own fit of AMS, and AMS, since it measures the positron fraction, it's very sensitive to dark matter decay into E plus E minus, of course. Although it's still sensitive when dark matter goes to mu plus mu minus, because the muon plus will further decay to E plus. And you still have some sensitivity to tau plus tau minus, but the problem is that the tau has a large hadronic branching fraction, so the sensitivity goes down a lot with respect to E plus E minus and mu plus mu minus. Nevertheless, if you look at the 50 GeV dark matter and you look at our AMS bound, you see that at 50 GeV, the bound is way stronger than the cross-section that you need to get the right relic abundance. So that means that you cannot get the relic abundance with these bounds if you take AMS into account. So AMS rules out these two guys here, right? I'm just going to talk about the 50 GeV, and later I'm going to say something about the other masses. So just look at the blue bars. Now, what about coupling to taus? The coupling to taus, if you look at Fermi-lat data, sorry, you see that at 50 GeV, the bound is slightly stronger than the relic abundance. So again, you cannot get the relic abundance using these bounds. You see that when you couple to the lepton doublet, the two sigma regions, oh, sorry, I forgot to say this, the shades of blue correspond to 1 for the dark, 2 for the medium, and 3 for the light sigma regions, right? Dark, medium, and light blue or green or whatever is 1, 2, 3 sigma. So the coupling to the doublets here, right, to the third family lepton doublets, although the 1 sigma region cannot get you the correct abundance, the 2 sigma region can, and the reason is that, remember that there is this square root of 2 factor here, right? The reason is that since you are coupling to the doublet, part of the cross section goes here into tau tau, but part of the cross section goes to nu nu. And the nu nu is not measured Fermilab. The same happens to light quarks, right? Anything that is not a B or a top. So if you look at the, again, Fermilab data, the bound is way below, well, somewhat below the relic abundance, so none of these guys can give you the right relic abundance. Similarly to BB, and what happens is that, oh, I forgot to say that since we are looking at 50 GeV dark matter, the coupling to tops doesn't matter because dark matter cannot go to TT bar. So if you take away all these couplings that I told you now, there are only two couplings left, which is the coupling to right-handed muons and left-handed lepton doublets of the second family, right? So to get the correct relic abundance for a 50 GeV dark matter in this framework that we are working, it doesn't matter. You always need to couple to the muon. So in some sense, this is telling you where to look. Also, it does not only tell you which masses are allowed, but it's telling you what final states you should be looking at to be able to enhance your sensitivity. Let's take a look at what happens for the 100 GeV very quickly. You see that most of the couplings here for the 100 GeV, most of the bounds from Fermilab, they do not beat, right? They do not exclude the relic abundance cross section, except for taus and quarks, right? Most of the quarks. And if you go back, just 1 second, if you go back to AMS, you see that at 100 GeV we are in the boundary of in the E plus E minus with respect to the relic abundance, but the other ones you just cannot put any bound. So basically, for the 100 GeV, you rule out all light quarks and you rule out the taus, but you can still get the correct relic abundance from coupling to, well, electrons, muons, etc. For half a TeV, then the data gets really, really worse, so there's not much you can tell, and basically everything here, everybody, or almost everybody, can give you the correct relic abundance. Let me say a few words about the other models. For the leptophilic model, so dark matter does not couple to quarks, you see that you can hide in the muon coupling. Right, so you see again that, for instance, for a 50 GeV dark matter, you get the correct relic abundance by coupling to muons or the lepton doublets of the second family. So this is why on that plot that I showed in the beginning, I will show you again, the leptophilic model is very similar to the general model because you are hiding when you go to low masses of the dark matter, you are hiding in the muon coupling. If you look at the leptophobic, again, as I told you, since these regions, these bars, they tell you the 1, 2, and 3 sigma regions, there will always be a 1, 2, and 3 sigma region because it is a delta chi-square, right? So it doesn't tell you how good is the fit. How good is the fit? It's going to be shown in the delta chi-square as a function of the mass that I showed you before, and I'll show you again. So in the leptophobic case, for the 50 GeV, you see that the coupling to third family quarks could give you the relic abundance, but nevertheless the fit is bad, right? So maybe you shouldn't look at the blue lines. For the green lines, it's better, right? And remember that you will always have a factor of 3, square root of 3, between the relic abundance and these couplings here because all quarks have color. Now, just a few words about the other two models. This is an interesting one. The family-oriented is the one where you have 3 couplings, one coupling per family. And you see that now the coupling, since the first family, the coupling of all first family fermions is dictated by only one parameter. You cannot go xenon-phobic anymore. So when you cannot go xenon-phobic, you see that the coupling to the first family here is very, very much constrained, even when you go to 500 GeV dark matter. So that means that the family-oriented will have a real hard time to hide in the first families. It needs to hide in the second and third family, and therefore, since the the relic abundance is going to be given by a combination of these guys. You are going to have an ellipse of allowed region in C2 and C3. I have this as a backup slide if somebody wants to take a look. And the last model is the last proxy, actually, is this flavor blind, where you have 5 couplings to right-handed charged leptons, left-handed leptons, right-handed up-type quarks, right-handed down-type quarks, and left-handed quark doublets. And you see that here again there is something interesting happening, that this coupling here always needs to be large, and it just cannot really go to 0, the coupling to right-handed up quarks. And the reason why it cannot go to 0 is just because the bound on the other couplings is very strong, right? At least for the 50 GeV. So since you cannot fulfill the relic abundance with the other couplings, you definitely need to fulfill with this one. All right, so let me show you my money plot again. So we see that the general and the leptophilic models, when you go from large dark matter masses to low dark matter masses, they behave very similarly, because when the masses start to get lower and the bounds start to get stronger, you can always hide in the muon coupling, right? And so below, for masses below around 20 GeV, you start to get really disfavored. And then for the other models, the disfavored regions happen about 70 to 50, below 70 to 50 GeV. And again, the reason is because since you don't have the muons anymore, or if you couple to the muons, for instance, in the family-oriented, you are also coupling to stranges and charms, etc. The bounds are much stronger. Let me just say a few words about important aspects of this study before concluding. So one important thing is the validity of the effective field theory. So here, there are basically 3 different scales that we are studying here. One scale is, for instance, direct detection, which is a very low Q square. Another scale would be the dark matter mass, because you have annihilation. So the Q square is about 2 times the mass of the dark matter, everything squared. And the third scale would be the LHC scale, for instance. So it's very important to assess the validity of the EFT to see if the whole fitting procedure and the whole framework still makes sense. Let me just go back a bit to show you something here. For instance, yeah, let's take a look at one of these couplings here. For instance, we can even look at the sigma C. The units here are in 1 over TV square. So you see that here, the coupling, I mean, at least the sum of these couplings needs to be about 3 over a TV square. That means that if you assume that your couplings are around 1, your scale, the scale that suppresses the dimension 6 operators, will be about a few hundred GeV. And this dark matter mass is about 50 GeV. So for both direct detection and annihilation is fine. If you look at this, this is for 100 GeV dark matter. Again, the scale is about 1 TeV. And if you look at this, although now the dark matter mass is at half a TeV, you see that the couplings are about 0.3 over TeV square. So the scale is above the TeV scale. So you are above the dark matter mass. So it looks like the validity of the EFT is fine. One can question the validity of the EFT for the LHC searches, but this is actually a completely different discussion because people are questioning that for some time. And we use an LHC search where basically what they do in a very fancy way is just to take, so whenever they have some high PT, let's say, event, which would break your EFT approach, they throw that statistics away, They throw that data away, and they only use a subset of data which still makes your EFT valid. That means that the LHC data, it's much weaker than what it could be, I guess. So in this specific framework, it doesn't play a very, very strong role. There are other things which maybe I don't have time to talk because it's 4:30 already. So but one can also question about the fine tuning. For instance, if you look at the direct detection, the xenon phobic line, one can question about what happens if you make a complete treatment of all these scales. I mean, using the running. So you assume that the parameters are something at a high scale, and then you run it down. So you're going to get an admixture of the high scale parameters when you go to lower scales. But basically what happens is that for direct detection, the most important, I mean, direct detection puts you a bound on the coupling to ups and downs, which is way, way, way stronger than any other experiment. So what is happening there is that even if you do this run, you are just going to find that a very non-trivial combination of parameters is going to give you exactly the xenon-phobic dark matter. So the running in this approach is not an issue exactly because we don't have comparable probes of the same coupling at different scales. There are also some comments that I wanted to make about flavor effects, since we are coupling differently to the first, second, and third family, but I guess I will skip that. But the bottom line is just that if we take the flavor effects into account, so the flavor effects, what I mean by flavor effects is just that if you couple differently to the first and second family, even if it's in a diagonal way, but not universal, what happens is that when you calculate loops, you can induce flavor change in neutral currents. But the problem is that if you want to calculate the loops to be completely consistent, you need to include the whole EFT basis. And if you include the whole EFT basis, you also need to include the off-diagonal entries, let's say the flavor changing operators. And when you do that, if you just do an unbiased fit, these flavor changing operators will try to compensate exactly for these loop corrections of the non-universal operators. So in this kind of approach, in the most general scenario, one may not really need to worry very much about the flavor effects due to non-universality. So I guess I can conclude. I still have some backup slides if somebody's interested about the searches or these degeneracies. But the main conclusion is that we analyzed the global status of the thermal WIMP dark matter in the context of effective field theory. It is a subset of the possible effective field theories that you could build, but we believe it's a meaningful first step. In some cases, we see that specific couplings are required to get the abundance, and this is very interesting because it tells you where to look to increase your sensitivity. And in general, for the leptophilic and general models, we see that masses below 20 to 30 GeV are disfavored, while for the other proxies, masses below about 50, 60, or even 70 GeV are disfavored. And that's it. Thank you.
Thank you, Pedro, for this interesting seminar. Now we should pass to the question round. Remember, you can question Pedro via the Google question and answer system. He also through Twitter with our hashtag. So let's check the question. We start with a question from Roberto Lineros that is asking the following. Do you include the bounds from antiprotons?
No, we don't. We didn't include those because why was that? I think when this paper was published, the bound was already there. but the main problem was the background, right? So modeling the background for the antiprotons is way more complicated than, I guess, anything else. So since we didn't really wanted to make a whole paper on the backgrounds of the antiprotons, we didn't include this bound.
Okay, we have another question also from Roberto. What does it mean 3 or 2 sigma bounds from below in the blue column?
So this basically means that for each parameter, we marginalize it over all other parameters. We find the best chi-square, and we calculated the delta chi-square of 1, 4, and 9, the 1 sigma, 2 sigma, and 3 sigma regions.
Okay, maybe there is any other question from the participants?
Yes, we have a question here.
Who? Roberto?
Hey, this is Ben.
Okay.
Yes, Herman has a question. Also, we have a question, but later, after Herman, we can...
Herman first. Okay. Herman, please.
Okay. This is Ben who has a question. Go ahead, Ben.
Concerning this xenophobic line, is there another experiment which uses a different element which would give a different line?
Yes.
So you can combine those?
So basically, we used Lux and Edelweiss, but the problem is that Edelweiss is about 2 or 3 orders of magnitude worse than Lux. I guess everybody who's not xenon-based experiment is about 2 or 3 orders of magnitude worse than Lux. So there's not really much you can do to break this degeneracy.
And with germanium? CDMS, for instance?
You can use germanium, but Edelweiss is germanium. But the problem is that the bound, if your bound is at the same level of Lux, then you break the degeneracy very well, somewhat well, because germanium is not super far away from, in terms of protons and the ratio of protons to neutrons is not so far from xenon. But the problem is that the bound itself from the germanium-based detectors is at least 1 order of magnitude worse, maybe even 2. Compared to Lux.
Okay.
So here I have a question, Pedro, for you.
Yeah.
So one question is like how you can deal with the resonances. I mean, I know that the AFT has the lack of, you cannot estimate where you could expect a resonance, and this is one of the main points from the people from LHC to criticize the method. But is it possible to include some kind of resonance behavior at some point? Like knowing that you have, at most, you're going to have the Higgs or some other mediators that in principle could be related in the dark matter?
We could have included couplings to the Higgs, right? Basically like, let me show you here. Where is this? So we could have included chi, gamma mu chi, Higgs derivative Higgs. So that could give you, for instance, dark matter coupling to Z's, right? Because if both Higgs gets a VEV, you get a coupling to the Z, or it could give you a derivative coupling to the Higgs itself. The thing is that, what do you want to do with this, right? So if dark matter is heavier than the Higgs, we have seen that if dark matter is above 100 GeV, the bounds get really weak. So even if you have this decay channel open, I'm not sure how much you gain with that. Of course, that the Higgs itself could mediate dark matter to, let's say, BB bar, but that would only be important, like really important, at the Higgs resonance. So it would be maybe at 125 GeV, or maybe, well, half of it, right? So maybe at 62 GeV, you would get a peak here in this chi-square, because if dark matter goes to the Higgs would go to these guys. But since this is a global fit, you would not see this peak at all because you could always, I mean, the fit would always set this coupling to 0 and prefer the other ones. So I don't think that the final result would change anything. It is still important to because the phenomenology is different, right? I mean, at colliders is different. I mean, there is this mono-Higgs search and etc. But I don't think at least this chi-square plot wouldn't change. I guess it wouldn't make your life easier anywhere, I think.
Okay, thank you. Just a very short. No, you have.
Yes, I have
there is
another
here
question.
Nicolas that want to do a question.
Yes, I have another question. It's a very simple one. Why did you consider those settings? Can you consider another settings to play with? For instance, with the different hierarchies in between the couplings you consider for first?
So, of course, we could consider, for instance, if you think about a Higgs-like portal or a scalar portal where the scalar mixed with the Higgs, you could imagine that these couplings would go proportional to the mass of the quark, well, the mass of the fermions. But since we are letting this thing completely free, I don't see how one could implement that, you know, unless you do like one coupling only or something like that. I mean, I'm sure that you could consider other proxies. That's true. But I mean, the thing is just the lack of space, right? We considered 5 proxies, and this is already a lot of stuff. So I guess you could consider more proxies, or you could even change this interaction, right? You could consider, let's say, a scalar interaction, or a combination of scalar and vector. But the point is that it's just so many operators that we decided to restrict ourselves. But there's no strong reason.
Of course, but I wanted to know if you could consider any other well-motivated guesses in order to test them.
Yeah, I guess so. I mean, let's see. On the time, we only thought about these ones because the only way of assuming some, I mean, if you want to do for instance, couplings that go with the mass, if you fix these ratios, this becomes basically one coupling, right? And then I think the whole approach is a bit less important because it's not. I mean, of course, it's still a global fit, etc. But a global fit of one coupling it loses a bit the meaning, right? But yeah, maybe one could think about other proxies.
Okay, thank you.
More question? I have one question. The analysis apply when the mediator, the vector mediator, is just the set.
Sorry, can you repeat that?
Yes, if the analysis apply when the vector mediator is just the set particle, the set one.
No, I don't think if it's the Z, it doesn't work because since we are using effective theory, we always assume that the mediator is in this thing here. We always assume that the mediator can be integrated out. So when you have dark matter annihilation, dark matter goes to the mediator, which goes to, let's say, fermion. The mass of this mediator is way larger than the Q square. It's going to be 2 times the dark matter mass. I'm going to hide you from my screen. So it could go to. The thing is that if you cannot integrate out the mediator, you cannot use this effective theory. And you can only integrate out the mediator if it's heavier than the dark matter mass. So this is not in the case that we are studying. So this wouldn't work for Z-mediated dark matter.
Okay, I don't see any other question around written by. Any other questions from the participants? Okay.
Very short. I mean, one question and maybe another stuff. No, but for instance, when you have this kind of setup, also you can transform your operator in other types, right? Like Pierce transformation. In principle, your same analysis would be you can apply it in other contexts, just by extension, no?
Yeah, you can fierce it. You can fierce it for sure. You could this operator could be equivalent to some combination of scalar, tensor, vector, whatever. but the physics should be the same, right? And
Right.
a Fierce transformation cannot change you the physics, so.
Yeah, that's the point. I mean, I was thinking that your analysis is also applied. You can apply it in many other contexts. I mean, it could be even more general than just for this.
Yeah, I think. I mean, the thing is that, so when you talk about EFT, you need to take away the redundancies of your basis, right? So there are three ways of taking away these redundancies. The first one is with total derivatives. So total derivatives are zero, and therefore if a set of operators is related by a total derivative, you can take one away of this basis. The other way you can do that is by Fiersing it, using Fierce transformation, right? Which is what you're telling. And the other one is using the equation of motion. So I guess you could do it, you could Fierce it, but you see that we never included any tensor or anything, any tensor interaction or scalar interaction. So to reduce the basis by using Fierce transformation, we would need to include the whole set, right? Dark matter, fermion with scalar interactions, vector interactions, axial interactions, etc., etc. Since we didn't do that, I'm sure that one can try to see how general this can be. You can probably put bound on some combination of operators, but it's probably not going to be an easy one-to-one correspondence.
Yeah, it makes sense. Yeah, it's not as general. And the other stuff that I want, if there is no other question from the rest of the people from the Hangout, it's just I wanted to congratulate about this introduction about your sets based on Feijoada. That was very, I like it a lot. It's very, very nice, very nice.
Well, this is what a global fit is, right?
Yeah, but it's more of it. Yeah.
We have another question from one of the viewers. Is this, could you prove this approach at the LAC too?
So so in this approach, the LHC bound is included. Well, it's for the LHC 8TV run. The LHC bound is included in the monojet search. Of course, that at the 14TV, well, the 13TV run or even the 14TV run, there will be an improvement of these monojet bounds. But my guess is that these monojet bounds are not going to improve like a factor of 10 in the scale that they are put in a bound, because most of these things, they have irreducible sorts of backgrounds which you cannot really get rid of. So I'm not sure that the monojets will play a major role from LHC run 2. Of course, that other searches may play a major role, but not the ones that we are including here, I guess. I mean, I did not study that in detail. Does that answer your question, or?
Maybe. There is no further question. Pedro, could you switch to your webcam, please?
Yes. Where's my webcam? And I see myself.
So, seems to be there is no more questions. So we thank Pedro and all our viewers, and hope to meet you again in the next seminar. Thank you very much. Thank you, Pedro.
All right, thank you. So should I disconnect, or I guess so, right?